Hello everyone. There is another method for avoiding the deadlock is there, that is resource allocation graph for deadlock avoidance. So initially we have discussed how we are avoiding the deadlock with the help of some additional information about the resources, as well as how we have to check whether the system exists in a safe state or unsafe state. For that we have to follow two steps. First step is we need some additional information about the process, which means how many number of resources it needs, and how what kind of resources it needs. So everything we are just requiring it as prior to the allocation of all the resources to the process. That is the first step. Second step is we have to follow some sequence of order of execution, but if you follow that particular order it should not lead to unsafe state. That we need to check it. So ensure the safe state of, ensure the safe state by following some sequence of execution in some order. In some order, we need to check it whether if you follow this particular order, it should not lead to deadlock. Okay. So the next type is, or the next method which we are following to avoid the deadlock, which is nothing but resource allocation graph. So already we know about what is resource allocation graph. So it is a graph which consists of vertices as the process, and the resources, and the edges which are nothing but how we have allocated the resources, otherwise how the process or requesting the resources. So in that way it represents the edges, right? So here in this graph also, we can detect easily whether deadlock can occur or not with the help of the cycle exist in the graph. If you have cycle, then we can say deadlock will occur. If you don't have cycle, then we can say deadlock will never occur. But even though if you have more number of instances for the same resource type, and this particular resource allocation graph represents we have only single instance for the particular resource type. For resource type R1 we have single instance, and for resource type R2 we have single instance. We don't have multiple instances of any of the resource type. If you don't have multiple instance, so if you are working with only the single instance of resource type, any of the resource type, then we can say, we can confirm that if you have cycle in the graph, if you have cycle in the graph, then obviously it will lead to deadlock. Okay, so surely it will lead to deadlock if you have cycle in the graph. But if you have multiple instance of the resource type, then we cannot say that, even though if you have cycle, we cannot say that deadlock will occur. It may or may not lead to deadlock. Okay, now we are actually working with the single instance, so we can say if cycle exists there, we can get the deadlock. So here in this graph represents we have two resource type, that is R1 and R2, and two process P1 and P2. So this particular edge is nothing but resources has been allocated to P1, so it is nothing but assignment edge. So the name of the edges also we know already. For the resource allocation graph we have actually two number of edges. One is assignment edge and another one is request edge. Okay, so this one is request edge, which means the process is requesting this resources. Process is requesting this resources R1. So we have one edge from P2 to R1, it is nothing but request edge. We have the edge from P1 to R1, it is nothing but I'm sorry, R1 to P1, it is nothing but assignment edge, which means the resource has been already allocated to this process P1. But here what is this dotted edge? So the dotted edge in the graph represents claim edge. So claim edge is nothing but in future this particular process P1 may request this resource R2. So this is what claim edge. So here it is represented with dotted line. Once if it requests this resource R2, then this claim edge will be converted into the request edge. This claim edge will be converted into request edge. So in the same way we have the claim edge in this other side also, that is P2 may also request R2 in future. So this is what the claim edge. So claim edge will be represented with dotted line. So it means in future we may get the request. So this is nothing but some additional information which we need all the time to avoid the deadlock, right? So here we don't have any cycle, so it is a simple graph which we cannot say that the deadlock will occur in the system. But if you have one more graph, So here it is a unsafe state in resource allocation graph. So if you look at this graph, obviously cycle may exist, and here we may get the deadlock. So how the cycle exists? So here P1 is actually allocated with the resource R1, P2 is requesting for resource R1, and R2 has been already allocated to P2. R2 has been already allocated to P2. Now P1 is again requesting, it is not the request date, it is the climb edge. It is the climb edge only, but at some point this climb edge may be converted into the request edge. If it converts to the requested edge, then obviously it forms the cycle in the graph. So climb edge represents in future the P1 may request this resource R2. So if it is converted into a request edge, then obviously we can say cycle exists in the graph and it will lead to a deadlock. So this is actually the unsafe state of the system. Unsafe state, okay, in this resource allocation graph. This is how we can detect it easily with the help of the resource allocation graph, whether it will lead to a deadlock or not, with the help of representing either safe state or unsafe state. Okay, if cycle exists in the graph, then we can say it is unsafe state, it will get deadlock. But because we are actually implementing the single instance resources, we are not dealing with the multiple instance. Single instance means there is only one instance, I mean only one copy of that particular resource type is available. So if you have only single instance, then obviously it will lead to deadlock if you have cycle in the graph. Okay, so very simple. So with the help of this resource allocation graph, how we are avoiding the deadlock, we can detect it easily and we can avoid it easily. So thank you.